I am Jay Kaushik, Principal Scientist at National Dairy Research Institute, Karnal, Haryana. Today I will be talking about the two related techniques, circular dichroism and optical rotatory dispersion.
Module on circular dichroism principle is covered under two different parts. This is part B of the module. It is advised that students understand the concept of optical activity and its origin in part A of the module and then proceed to part B.
First we will take the example of linear or plane polarized light. If you see the source of lights, a halogen lamp, natural light coming from the sun or any star or any tube incandescent lamp, so they are all source of incoherent lights, and the light, it vibrates, it oscillates in all the direction. So therefore they are not polarized lights. So how to produce the polarized light? First we have to purify the lights of a given wavelength, that is done by the monochromator. Once we purify the light at a given wavelength, this is polarized through a slit. Slit is such that only waves vibrating or oscillating in only one direction, they will pass through it. You can see the vertical slit shown in red color. The second one, horizontal slit, it's shown in green color. If you have to produce linear or plane polarized light, they are the same thing. We have to pass them through these slits. The panel A on the top, this is the light which has passed through vertical slit and now propagating from left side to right side. So this is a typical sinusoidal wave. Similarly, we have second wave whose oscillation plane is horizontal. So similarly, we can produce light oscillating in any direction. Now see, if we superimpose, if we allow these two lights, one is oscillating in the horizontal direction, another is oscillating in the vertical direction. If you superimpose them, then how do they interact? So there can be, you might have read it earlier, we already know constructive and destructive interference. Here they are going partially constructive if they are in phase, or if they are out of phase, they will go partially destructive interference also. In this particular case, both the waves, horizontal and vertical, they are in phase. So therefore, the resultant wave is also in phase, but the amplitude is different, as well as the axis of oscillation or plane of the oscillation has changed. So this is the case of production of linearly polarized light and their superimposition resulting into a new wave. This slide shows the differential interaction of plane polarized light with optically active medium. You can see the incident light, it is a plane polarized light, not a circular one. When it is passing through the medium which is optically active, the linearly polarized light, they interact with the medium in a particular way, such that the plane of polarization is rotated toward one side. The rotation direction depends upon which particular component is affected to a greater extent. Affected means when these lights, component lights are passing through the optically active medium, one will experience a greater refractive index than the other one. So this leads to slowing down of the velocity of that particular component. And now we will see again what is the meaning of rotation. Differential interaction of plane polarized light with optically active medium. If you place an absorbing material between the two windows shown in previous cases, so that the material preferentially absorb only vertical component, the intensity of this light component, that is the amplitude square, falls exponentially with box, or you can say the cuvette path length. You may notice another interesting phenomena going on in the box. The resultant wave shown in blue color is continuously changing the orientation of the electric vector with respect to electric vector of the component lights in such a way that it seems rotating toward the electric component of non-absorbed horizontal wave, that is the green light. If you observe from right side window such that light travels toward you, you are standing on right side and light is coming from left side to right side. The blue color light seems rotating anti-clockwise. The blue color light seems rotating anti-clockwise and is known as left-handed rotation. If horizontal wave is absorbed and vertical component does not, the resultant combined wave shown in blue color will seem rotating clockwise from observation window where you are standing, and it is called as right-handed rotation of the light. In real situation, both components may be absorbed to different extent, resulting in the rotation of the electric vector of the resultant wave toward the light component absorbed in smaller amount, that is toward the bigger component vector. Once the light emerges from the absorbing box, no further change in the polarization direction of the light takes place with respect to component lights. In the previous slide, I introduced you to the linear polarization and how it interacted with the optical media, and when we should say that it is left-handed rotation or right-handed rotation. In this slide, I will introduce you to the circularly polarized light. There are two kinds of circularly polarized light: left-handed circularly polarized light or right-handed circularly polarized light, which I introduced you earlier. Let's talk about the left-handed, how to generate it. In the previous case, we produced linearly polarized light by purifying it through the slits or some other mechanism. One is oscillating in horizontal plane and another is oscillating in vertical plane. If you introduce a phase difference of 90 or say pi by 2, then what will happen? You will see in panel A, when vertical component is reaching to the maximal, the horizontal component or horizontal wave is reaching to 0. That indicates they are differing by an angle of 90 or their phase difference is 90. In this case, the resultant wave, because of the superposition of these two waves, is rotating anti-clockwise. If you are standing on the right side watching the wave coming toward you, you will see the resultant vector, which is shown in blue color, is rotating in anti-clockwise. So this wave is called left-handed circularly polarized light. Right-handed circularly polarized light. If the horizontal light has a phase difference of minus lambda by 4 or minus 90 degree with respect to vertical light, superimposition of the two lights results in right-handed circularly polarized light, that is shown in blue color. So now we can see how to produce left-handed circularly polarized light and right-handed circularly polarized light. We superimposed linearly polarized light. One was oscillating in vertical plane while another was oscillating in horizontal. When they were superimposed and if there was no phase difference between these two, they produced another linearly polarized light. and this was at an angle of 45 to both of the components. Now we will introduce you, if LCPL and RCPL they superimpose, what happens? Superposition of LCPL and RCPL results in linearly polarized light. So that's very interesting that we combined linearly polarized light to produce circularly polarized light. Now if we again superimpose left-handed and right-handed circularly polarized light, they again result into a linearly polarized light, or say plane polarized light. The blue component in panel B shows how left-handed and right-handed, which are shown with the two vectors rotating in clockwise and anti-clockwise, they combine together and produce a new wave which is oscillating in horizontal direction and shown in blue color. Now we will allow these two lights to pass through an optically active medium to see how do they interact with the optically active medium. LCPL and RCPL experience differential refractive indices in an optically active medium, resulting in their differential velocity and hence wavelength in the medium. So this results into a rotation of the plane of polarization. Differential velocities of LCPL and RCPL in optically active medium results in the rotation of the plane of polarization of the combined light. So that is what we discussed earlier also. For simplification in these figures, LCPL and RCPL absorption is kept at 0. Otherwise, rotation and absorption occurs simultaneously. You will see in panel A, it is the left-handed circularly polarized light, in panel B, right-handed polarized light, and when they are superimposed in panel C, they are traveling along the same path and through an optically active medium. You can see that the wave shown in blue color, which is the resultant of the two components light RHPL and LCPL. So that is linear, but now it is changing its direction of oscillation. From horizontal, it is making an orientation toward the left side. So if you see the blue component at the entrance and at the exit, so they are at an angle, and this angle is, we already know, that is the alpha. In the last case, I showed you when the refractive index of the two waves which are passing through the optically active medium are different, what happens with the resultant wave. So that is oriented in a different plane. Now we will see, if let's assume that there is no rotation of the resultant wave, but only absorption. That is not possible, but for simplicity we will show that the refractive index is similar for the two component waves, but it is the absorption. LCPL and RCPL experience differential absorption in an optically active medium, resulting in their differential amplitude in the medium. If the amplitude are different, they will affect the resultant wave. And how it is affected, you can see in the panel starting from A to B. In panel A, it is the LCPL, left-handed circularly polarized light, while panel B shows right-handed. So here what I am trying to show is that the optically active media is differentially absorbing only right-handed component of the light, while left-handed is not absorbed. In reality, both can be absorbed, but to varying extent. But here what I am showing is left-handed is not absorbed, but right-handed is absorbed. And you can see when left-handed is passing through the optically active medium, there is no change in the wavelength, in the velocity, or its absorption or electric vector. They are the same, and the position of the electric vectors at the incident window and at the exit window, they are parallel or superposed over each other. That means there is no change in the rotation. That I did for the sake of clarity. Otherwise, there will be, if there is a optically active medium kept in between these two. And if you move to the second panel, in which the RH right-handed light is passing through the optically active media, in that case it is being absorbed in an exponential manner, just like the Beer-Lambert law. So when the path length increases, the light is absorbed exponentially. But once it is out of the box which contain the optically active media, there is no change. And you can see when both A and B panel are combined, that is LCPL and RCPL, both are combined together, and after passing through the optically active media, how the resultant wave is behaving. It is rotating around the axis, which is horizontal in this case. So rather than oscillating on the horizontal axis, it is now oscillating around this particular axis. Now rather than following a linear oscillation path, it is following a elliptical. So this is the ellipticity we are interested in to measure in circular dichroism experiment. In the previous two slides, I showed how the left-handed circularly polarized light and right-handed circularly polarized light interact with the optically active medium. At one time, I showed only one phenomena, optical rotation or absorbance of one of the component to a larger extent than the other one. But in reality, an optically active medium will absorb as well as it will rotate the light. In this slide, I am showing LCPL and RCPL experience differential absorption and refractive indices in an optically active medium, resulting in their rotation and ellipticity. So on the bottom, I am showing 4 panels. So the first one is the incident light. In this case, LCPL and RCPL, they are rotating in opposite direction, while the resultant vector, it is oscillating linearly, or we can say this is a linearly or plane polarized light. When this light is introduced into a medium which is optically active, and let's assume the right-handed component is absorbed to a greater extent, then what we see at the exit is shown in panel number 2. Here you can see the right-handed component is smaller as compared to when it was there in the incident light. So this smaller amplitude indicates that a part of the light has been absorbed by the optically active medium, while the electric component of LCPL, represented by the vector in red color, it has not changed. But when both these waves are combined, it results into a new wave which is oscillating around the horizontal plane, and this is the ellipticity. And we measure this particular property of optically active medium by a circular dichroism machine. But in this case, what I am showing is only one part, that is the CD phenomena. Now let us see panel number 3 in the bottom. Here LCPL and RCPL are not absorbed, but they have different velocities when they are passing, traversing through the optically active media. So that which I explained earlier, this results into rotation of the resultant wave in a particular fashion, and that will depend upon which particular component of light, that is LCPL or RCPL, are experience a greater refractive index that leads to decrease in their velocity and hence creating a phase difference as compared to the other wave, and this leads as if it look like that the plane of the linearly polarized light is rotating, that is the resultant light. Now we will move to the more complex example where in real world both the phenomena ORD and CD are taking place, or rotation as well as absorption of light is taking place. In this case, electric vector of light at the exit of the medium with higher refractive index and absorbance of RCPL is taken into account. So you will see that RCPL is not only smaller but it also experience slowing down while passing through the medium, and therefore it is not only making a ellipse. So far we discussed about the circular dichroism and optical rotatory dispersion and how to create or generate lights oscillating in a particular plane or in a circular path. Now understand this one, we can move over to the presentation of circular dichroism data, like what are the units in which CD signal can be shown. The CD machines acquire CD signal as a function of either wavelength or time, and CD signal is shown in terms of ellipticity in millidegrees, because the change in ellipticity or the ellipticity of the ellipse is usually in millidegrees. The change in absorbance is not so high between the LCPL and RCPL. Both the values are very large, but the difference between the absorbance is small. So we are trying to get this information, very small change from the large noise. So that is done by specific filters that I will be talking in another presentation. Now let us see, we have recorded the data. How to present this data? The data was obtained as millidegree versus wavelength or millidegree versus time. The CD signal should be normalized to path length of the cuvette and concentration of the sample, because different laboratory collect data in different sizes of path length of cuvettes as well as different concentrations, but when we report the data, we have to report the data in a standard form, and this standard form is called the molar ellipticity for CD, or for ORD experiment we can say molar rotation. The normalized ellipticity is then called as molar ellipticity, and normalized rotation is called the molar rotation. Molar ellipticity is written as theta enclosed in the brackets and can be defined with respect to molecular weight or say concentration. You can see the equation shown in red color. Molar ellipticity theta is equal to 100 multiplied by theta observed divided by path length, that is the L, and concentration, that is the C. The unit of molar ellipticity is degree centimeter square per decimole, where theta observed is the observed ellipticity in degree and is usually recorded in term of millidegree and should be converted to degree before conversion to molar ellipticity. L is the path length in centimeter, C is the molar concentration in mole per liter. The D mole unit indicate decimole by convention. If we see, protein is a soup of amino acids, or it is a polymer of amino acids, and one protein differ from another one in their number of residues. So it can be a good idea that we normalize the length of the protein also with the number of residues. so that we can calculate molar ellipticity per residue. So this is called as the mean residue ellipticity or MRE. So simply one can divide the molar ellipticity by the number of peptide bonds, that is n minus 1. N is the number of residue and number of peptide is the n minus 1. So here protein is treated as a solution of amino acids and molar ellipticity per residue is calculated. It is basically normalized molar ellipticity with respect to size of the protein, essentially providing idea about CD signal per residue. For estimating the secondary structure of proteins, a normalized molar ellipticity independent of protein size, that is the MRE, is more meaningful. And many of the online server like Dichroism, when you go and try to calculate the secondary structure of protein, it only accepts MRE as a value, or you can directly input some data which is received directly from the circular dichroism machine and give the path length of the cuvette as well as the size of your protein and the concentration of your protein used during the experimentation. In visible region, some paper describes CD unit in term of absorption, and earlier also I talked about that there is a relation between the ellipticity and the differential extension coefficient or extension coefficient of the LCPL and RCPL. So the delta epsilon is the difference in the extension coefficient of left-handed circularly polarized light and right-handed circularly polarized light. So if we take this difference and multiply it by 3298, then we get the ellipticity, where these parameters are defined. Epsilon is the extension coefficient, epsilon L is the extension coefficient experienced by left-handed circularly polarized light in the medium, and ER is the for RCPL. The unit of delta epsilon is the same as extension coefficient, that is per mole per centimeter. So far we have covered circular dichroism and optical rotatory dispersion. So now we are reaching to the end of this presentation. On the summary part, what we discussed in this lecture are the following point. Asymmetric molecules are optically active, which means that they will differentially interact with two components of light. They are LCPL and RCPL. LCPL and RCPL are in themselves asymmetric with particular handedness. These asymmetric lights induces helical motion in charged particle in asymmetric molecule, resulting in the optical properties of the material. Apart from structural asymmetry, CD and ORD also originates from conformational asymmetry in molecule peptide bonds in case of proteins. CD originates from differential absorption of LCPL and RCPL by the optically active medium. The CD is expressed with molar or mean residue ellipticity. ORD originates from differential refractive indices of LCPL and RCPL in an optically active medium. This changes the velocity and wavelength of the light to varying extent, resulting in the rotation of the combined light when it exits from the medium. Furthermore, rotation depends upon the wavelength. CD and ORD are interrelated properties and can be derived from each other by integral transform known as the Kramer-Kronig relationship. Because the origin of these two optical properties is the same electronic system in an optically active media. So that was all for today, and now we will conclude that we have reached to the end of this lecture with the summary in the previous slide. Now we can conclude this lecture. So what we learned in this lecture was that what is the optical activity, how it is related to the asymmetry in the molecules, and how to make use of circular dichroism and optical rotatory dispersion to determine their chirality or asymmetry or their conformation or structure. So these two techniques are interrelated because they are originating from the same electronic system of the achiral center. So even if we have data from one, it can easily be converted into another one. We also learned how to produce linearly polarized light and circularly polarized light. How do they differ from each other? So what are the major difference between the two? So that was the idea for this lecture, and when to use these two types of light to determine the structures of biomolecules. So in the next lecture, I'll be talking about the use of circular dichroism and ORD for determining the structure and conformation of biomolecules like DNA, protein-protein interaction, protein-DNA interaction, different types of DNA. So that we will see in the next chapter. Thank you for your patience, hearing, and I hope this lecture will help you to understand circular dichroism and ORD in better light. Thank you.